Hi and welcome back to my channel. So this video is a continuation of my previous episode number 56 where I showed how to measure the noise figure in that case of my HP 8591E spectrum analyzer. So unfortunately I noticed that in this video I used by mistake the wrong microphone. So I used the microphone of the camera rather than this microphone here. And so the audio quality is unfortunately a bit poor, but okay, it's still audible, so I decided to not remake the entire video. Anyway, so what has been done in that video is measure the noise figure. And basically the setup, just to summarize very quickly, I connected a 50 ohm load to the input of the spectrum analyzer, and then I measured, as you can see, using this marker noise functionality, I measure the power density of the noise. In this case it's minus 151 dBm, as you can see there. And that is actually pretty good. So I was looking at other spectrum analyzers. So this is, for example, a Rode & Schwartz new a spectrum analyzer for about 8,000 euros, so very expensive. And as you can see, the numbers are pretty similar actually. So my HP gives minus 151, so that's pretty good. Other spectrum analyzer like this Siglent, which is very popular, and it's a good new device for about 1,500 euros, has lower values, as you can see here. So in the it would measure about it would be about 10 dB less sensitive than my HP. However, as you can see here, the new amplifier, the new spectrum analyzers also have the option to activate a preamplifier. Okay, and my HP does not have an amplifier. And so this is one of the reasons now I want to measure the noise figure of this amplifier that I can use to increase, for example, among other things, I can use this to extend the sensitivity of my spectrum analyzer. And so how are we going to do that? So let me show you just a little bit of paper here. The measurement, as we have done last time, as I said, we connected a 50 ohm resistor to the input of the spectrum analyzer. So the idea is that this resistor produces some thermal noise, and this thermal noise is known from physics, so we know how strong it is. It's basically minus 174 dBm in power, okay? And so we send it to the input of the spectrum analyzer, and the spectrum analyzer will have some internal noise that we can model as some additional input that goes to the input of the spectrum analyzer. And so looking at the figure that, the noise density that we measure, minus 155, we can basically fully characterize this spectrum analyzer noise, because we knew what was coming from the resistor, and so the rest must come from this internal noise. And that's what the measurement basically what I measured, right? And from this value, minus 151, I explained in that video how to calculate the noise figure. The noise figure is just the difference between minus 174 and this value, so 23 dB. And the noise factor, so the noise factor is the inverse of the logarithm of this 23. And other values, so there is also the thermal noise. There are all equivalent values. Now when we have an amplifier to measure, we can already use these numbers that we have already calculated and put the amplifier in the middle. So I'm going to connect a 50 ohm load to the input of the amplifier. This amplifier will have some amplifier noise that we don't know. This amplifier is a 40 dB amplifier, okay? So it amplifies the signal by 40 dB in power, or equivalently by, this should be 10,000 times linearly. So 40 dB means 10,000 times greater. And then the output of this is going inside the spectrum analyzer, which also will have its own noise that we already measured. And so we will read something. And what we are going to read is really the sum of all these three noises, okay? But since we know 2 out of 3 of these noises, because we already measured them, we will be able to identify and characterize this noise here, which is what we want to discover. So let me prepare the experiment, basically. So I'm going to connect the 50 ohm load directly to the input of the amplifier. Okay, just like that. And then let me find some coax cable. Okay, and I'm going to connect the output to the input of the spectrum analyzer. Okay, so now we are measuring. As you can see, the noise floor is changing. So let me actually reactivate the spectrum analyzer. It is going up. So let's wait until it stabilizes a little bit. In fact, let me stop the averaging and restart it, so we don't need to wait. So trace, video average off, and let's start it again. Okay. So as you can see, the response is not that flat now. It's more jumpy here. And so the noise behavior of this amplifier is not perfectly flat. Okay? It has some differences in frequencies. At the moment we are, as you can see, at 75 megahertz. By the way, this amplifier works from 0 to 150 megahertz, so we are in the middle. And so, yeah, let's make the calculation, in fact, at 30 megahertz. 30 megahertz because I already verified in my previous one of my previous videos that at 30 megahertz the amplification is precisely of 40 dB. Okay, so it's very accurate there. And so here we are reading, as you can see, in a noise density of minus 119.4. So let me write it down. So we are reading minus 119.4. Okay, so that's all we need to verify. And let's go back here to the calculations. Right. So sorry for this cable. Right, like that. So what we measured here is this. Okay, so this is the measurement that we had. And again, this is reading basically the combined noise of all these things. So from this value we can extract the noise figure of this whole system, basically the amplifier together with the spectrum analyzer. However, before we do that, so let me move a little bit this cable, which is a bit annoying. Okay, like that. So here, however, we have to keep in mind that this amplifier is amplifying by 40 dB. Okay, so what we read here at the input of the spectrum analyzer is in fact, well, this value, but we need to take in consideration that the input is amplified 40 dB. Okay, so in fact I can instruct the HP to do this calculation by itself. So I can go to amplitude, external preamp, so I can basically inform the spectrum analyzer that there is a 40 dB amplification going on at its input. So let me write that, 40 dB. And okay, so as you can see now it's compensating for that, and we get a reading of minus 159. Okay, so basically it's measuring at this point minus 159.4 dBm. Okay, so right, so it calculated that if it was minus 119.4 here, well, this came after a 40 dB amplification, so the signal here, the noise, was at minus 159.4 dBm. Okay, so the noise figure, therefore, of this value is the difference between this value and this value here. So it's going to be noise figure of what is the difference here is 14.6. Okay, so 14.6. Right, and now we want to calculate the noise factor, of that. So the noise factor, well, we can calculate it as 10 to the 1.36, but let me actually stop the video a second and activate the website to make the calculation so it's easier to follow. Okay, so I just loaded the equation here on Wolfram Alpha. So I'm basically asking what is the f such that the 10 logarithm base 10 of that f give us 14.6, and the answer is, as you can see, is 28.84. Okay, so so basically this is 28.84. Right, so now we have characterized the noise figure and the noise factor of the system composed of the amplifier and the spectrum analyzer together, okay? And now we have to discover how to characterize just the amplifier noise. And to do that, we are going to use an equation called the Freeze equation. So let me show that to you. You can find it in Wikipedia under noise figure page. And basically says that if you have a cascaded situation where you have, for example, several amplifier, 1, 2, 3, 4, at the end, for example, a spectrum analyzer, well, you can compute the noise factor of the whole system by using the noise factor of the single amplifiers and together with their gain. Okay. In our case, we have only two things. So the first thing is the noise factor f1 of the amplifier, and the second thing is our termination, so the spectrum analyzer. And the gain that we have is of 10,000, okay? This is the gain linear, not in dB, of the amplifier. So if I go here, this is the equation I set up. So f was the whole, so let me show it to you again. F is this noise factor of the whole system, okay? Right. The noise factor of the spectrum analyzer, so of the last component, the second component, I already calculated in my previous videos, is 200. And so I can use this information to set up the equation, and I have that the whole factor is going to be an unknown, so this is going to be the factor of the amplifier that I'm trying to discover, plus 200 minus 1, so 200 is the noise factor of the spectrum analyzer, divided by 10,000, which is the amplification of my amplifier. And then I'm also taking expressing this value A in dBs and calling it B. And the result is this. So A is going to be 28.82 and B 14. Okay, so let me write it down. So here I have a noise figure and noise factor. So noise factor is 28.82. And the noise figure, we said, I already forgot, is of 14.59. Let's call it 14.6. Okay? 14.6. Now, as you can see, in fact, that these values, so all are very similar to the values they already measured for the whole system. And this is because the noise figure and factor of this amplifier are much lower than the noise figure and amplifactor factor of the spectrum analyzer, okay? So they dominate the equations. Anyway, these are now the precise informations about my amplifier. And now, as you can see from this equation, let me make this point. It's important to observe that the noise factor of the second and third and fourth components in a chain, it's way less important than the first amplifier, okay? Because they get discounted, divided by the gain, in this case 10,000, okay? So really the whole noise that you have in a chain of amplifications and stuff is basically entirely dominated by this first amplifier. And so concretely speaking, this means that in my setup now, the noise of the system composed of the amplifier and the spectrum analyzer is basically just the noise of the amplifier, which is lower than the noise of the spectrum analyzer. And so this means that I have indeed increased the performances of my spectrum analyzer, at least in the frequency range covered by this amplifier. And indeed we are reading now a noise density of minus 159. And again, if we go back to the datasheet of this very expensive Roden-Schwarz spectrum analyzer, when you use the preamplifier on, they have this figure. So it's basically we are on more or less the same. So this looks like slightly better, 5 dB better or something, but we are around this value. So the amplifier definitely helps in increasing sensitivity. So there is another point I want to discuss. So we discovered that the noise figure of this amplifier is 14.6 dB, and its noise density correspondingly is minus 159.4 dBm per hertz. Okay. If you have seen my previous video about episode number, I think, where was it? Episode, yeah, 56. At some point I discussed how it's possible to express the noise density not in dBm, which is a measure of power, but in nanovolts, which is a measure of the amplitude of the voltage, okay? Of course, the two are related in a quadratic expression, but anyway, this is discussed in my previous video, but equivalently, this noise density can be expressed as 2.4 nanovolts per square root of hertz. So let me show you the calculation to do that very quickly. Where is it? So yes, I'm saying basically this is my noise density in dBm. And from it I extract the corresponding power in watts. Okay, P is the power in watts. Then when expressed to dBm, which is means this formula here, gives me minus 159.4. And then I simply use the relationship between voltage and power to extract the number 2.4 basically nanovolts. Okay, I mean this is expressed in volts. And so to the power 10 to the power of minus 9 gives me nanovolts. Okay, so this is the expression that we have here. And then given this density, we can obtain the noise present at different bandwidths, okay? So as I explained in my previous video, the noise depends on the bandwidth that you look at. The larger the bandwidth, the larger the noise. And for example, here I have computed the noise expected at 150 megahertz. To be, the expected noise is 29 microvolts. And the expression to do that calculation is this. So, you know, we just multiply the noise density, which is valid for 1 hertz, to the square root of the bandwidth that we are considering. And so, yeah. We have the noise density multiplied by the square root of 150 megahertz. And that gives us, you know, the number that you can see here, 29 microvolts. Right, and I can do the same calculation, of course, for arbitrary bandwidths. For example, at 20 megahertz, I get 10 microvolts. So let me show you quickly. So if I go here and instead of 150 megahertz I write only 20, I get indeed about 10 microvolts. Right, so why I did this calculation for this specific bandwidth? Well, this is to compare the results that we have with the official datasheet of this amplifier. And so let me show it to you. The datasheet is here. And as you can see here, we get at 150 megahertz. The equivalent wideband is 150 megahertz because this is the basically the bandwidth of this amplifier. The input noise level is of 40 microvolts. Okay, so the reading that we have is compatible with the datasheet. I mean, in datasheets they always write worst case scenarios, guaranteed values rather, and so this amplifier is a bit better than specification. It's only 29 instead of 40 microvolts. And the value calculated for 20 megahertz is useful because we could have checked the noise floor of the amplifier just using a very basic oscilloscope. So this oscilloscope that I have here is of just 20 megahertz of bandwidth. Okay, so it's a very simple oscilloscope. And so let me show it to you what happens if we measure well, just what is being produced now by the amplifier. It's noise basically when the input is just terminated by a 50 ohm load. So let me connect it and see what happens. So this is the noise that we are visualizing. At the moment, the graticule here is set to 50 millivolts per division, and this is what we see. Okay, so it's that line there, and so I cannot do a precise measurement because of how big it is, but what I can do is produce some noise using my signal generator. And so I'm going to produce some noise at exactly 1 millivolt. 1 millivolt, by the way, is so let me show that to you. Here we have 10 microvolts of input noise, equivalent input noise, and the amplifier is increasing. It's a 40 dB amplifier. Okay, so 40 dB in power amplification means 20 dB in voltage, and 20 dB means 100 times. So really what we get at the output of the amplifier is this value multiplied by 100, which is 1 millivolt. Okay, RMS. So the noise at the output that we expect after this calculation should be at 1 millivolt RMS noise. And so I can produce this with this Siglent SDG1032X signal generator. So let me do that, and I've already connected the cable here. It's set, as you can see at the moment, to produce, I don't know if you can see, is set to produce, let me see, 1 millivolt, so I don't know if, 1 millivolt, right? And so it's going to channel 2, so let me go to channel 2 at the moment and activate the signal generator. And as you can see, something very similar in shape, right? It's a 1 millivolt noise. And notice what happens if I move, for example, to just 2 millivolts. So it gets much larger, okay? So we get that 1 millivolt is a signal of this shape, and it's precisely what we get. It's essentially the same of what we get from the amplifier, as you can see. So this is a very rough measurement of the noise generated at 20 megahertz of bandwidth that you can do with just a basic oscilloscope. We didn't need the precision of a spectrum analyzer, and we could have basically obtained the same results with just an oscilloscope, and in fact a very basic one. If you have an oscilloscope, for example, of 100 megahertz, instead of computing here the value for 20 megahertz, you should compute the value for 100 megahertz and so on, with different bandwidth of your oscilloscope. Anyway, the conclusion of all my experiments regarding this amplifier is that it is completely within specifications, and it is not a low noise amplifier. So the noise figure we have measured is of as you can see 14.6. There are amplifiers, so let me show you on the fly here. If I go to mini circuits, for example, and I go to products, amplifier, and I select low noise amplifier, well, many amplifiers that they have noise figures of less than 3, as you can see here, okay? So basically this is not really a low noise amplifier, it's a linear amplifier, but it's already great in that it increased the sensitivity of my spectrum analyzer to, you know, to basically the specs of this very expensive you know, type of new spectrum analyzer that we have here, at least on you know, up to 150 megahertz, which is the limit of this amplifier. And of course, if I had an amplifier of let's say just 3 or 4 dB of noise figure, I will get basically 10 dB better noise response on the spectrum analyzer. So anyway, so I hope this video was useful to you, and for sure it was interesting for me to learn all these things, and also to spend some time you know, making these videos. And I hope it was useful, and I'll see you next time. Bye bye.